In this project, we have been working on a system named the ReDiCom, which aims to provide flexible and convenient communication for the first responders. This system uses a layered architecture and is implemented with a modularized design similar to the 5G access network. In the application layer, we provide two applications. The messaging app allows the incident commander dynamically instantiate a command chain based on a template, and the first responders involved can then send messages to different groups of people at different granularity. This allows the information to be delivered to only the units that need it. To achieve this feature, our information layer performs name expansion on a graph-based namespace. The network layer and link layer cooperate to enable communication in infrastructureless environments using D2D links. The coded computation app allows the first responder to distribute computation-intensive tasks to nearby helpers to accelerate the processing. Please refer to our presentation video for more detail about the messaging and coded computation apps. In this demo, we're going to show 4 new features added to the system, namely the map tool, the consensus protocol, the D2D text-to-speech capability, and the dynamic routing protocol. The map tool allows the first responders to distribute the tasks and communicate based on the geolocation and add markers to different locations while performing tasks. When creating an incident, we have now added a location placeholder in each pre-plan. The location-based names are shown in the green color. When the pre-plan is instantiated, the location placeholder is also added to the namespace. Now let's assume that the dispatcher has dispatched several units for the incident commander. Please refer to our presentation video for the detailed dispatching process. The incident commander can now go to the map page for the location-based communications. We used control from Mapbox since it has pretty good offline map support. This allows first responders to pre-download a part of the map before going to the infrastructureless area. We allow the commander to modify the names of the locations and edit the shape of each area. To create a shape, he can long press on the map to add points, move the points by dragging them, and close up a shape by adding a point close to the first point. Once a shape is created, he can also modify the shape. He can long press the edge to add a point, then drag the points to the desired locations. To remove a point, he only needs to move the point close to one of its neighbors. Once finished, the application would recenter the area in the map. We also allow the commander to create sub-areas and form a hierarchy based on the geolocation. Let's create a sub-area called East now. Under East, we create 3 sub-areas named East North, East Mid, and East South. Since the 3 sub-areas already fill the area East, we can make East shapeless. The application would use the sum of its children areas as its shape. When any children area is modified, the shape of this area will also change accordingly. By default, the application generates a random color for each area, but the commander can also change the colors as needed. Let's assume that we have also created area West and some sub-areas. We can see that when the incident commander is creating the areas, the application creates location-based names according to the area hierarchy for the location-based communication. On the right side of the map view, we have an expandable messaging panel so that the commander does not have to switch back and forth between map and messaging apps. Now the commander can assign units to different areas. By clicking the Assign button, we list all the units dispatched to this incident, and the commander can assign units by simple clicks. For the units that are not dispatched to this incident, the commander can request units from the dispatcher similar to the messaging app. When assigning a unit, the application sends a message to that unit with the area name carried. By long pressing the area name, the unit can navigate to the map application and have the area highlighted and centered. Here, we assign EMT1 and Field Officer to East, Firefighter 1 to East North, Rescue 2 to East Mid, and EMT2 to West. The names are listed in the area hierarchy view. When assigned to areas, the first responders can add markers by long pressing the desired locations. For each marker, we allow the unit to choose a type of the marker defined by the pre-plan and add a short description to the marker. Firefighter 1 is now adding a marker in area East North. Once he finishes editing, the marker can be seen by the first responders along the location hierarchy, namely units in East North, East, and Jersey City. But Rescue 2 and EMT2 do not receive it since they have been assigned to East Mid and West, which are not in the location hierarchy. The first responders can also click the markers to see the detail, which includes the location, the type, the unit and time that created or updated the marker in the latest description. The first responders can also communicate based on the location hierarchy. When the field officer sends a message to East, all units dispatched to East will receive it. This includes EMT-1, Firefighter 1, and Rescue 2, but EMT-2 does not receive it since he is dispatched to West. We also allow first responders to update the marker according to the situation. Here, EMT-1 is modifying a marker added by Firefighter 1. The update is also seen in the location hierarchy. Here, we have two different propagation requirements on the same name hierarchy. The marker information should be propagated to the parent and ancestor areas, where the messages should be propagated to the children and descendant areas. In our application, we create two sets of names with opposite directions among names. The application would send marker information on the topic hierarchy names and the messages on the recipient hierarchy names. Since we use a namespace based on directed graph, we unify the requirements into one single rule, forward data based on the direction of links. Now let's assume that the first responders have added many markers in different areas. We show the marker count on the right of each area. When selecting the area, we show the count of each type of markers. The commander can click a type to show or hide the marker of this type. By long pressing the type, the commander can also show only this type of marker or review all the markers. The map application can also work in infrastructureless environments. We assume that the shelter is far away from the coordination center. We mimic it by disconnecting the Bluetooth link between the patrol car and the rescue one. Now commander adds a new area in the east and assigns rescue 2 to the area. No unit in the shelter sees the update since they are not connected, but the information is buffered on the patrol car. When the patrol car moves to the shelter, we mimic it by disconnecting the Wi-Fi on the patrol car and connect it to rescue 1 via Bluetooth. The new area and the assignment is seen by the units assigned to East and also Rescue 2. Rescue 2 can leave the shelter and search the new area. We see that when not connected, the marker added by Rescue 2 is not seen by the other units. But when Rescue 2 comes back to the shelter, EMT-1 and field officer can see the marker. Similarly, when the patrol car goes back to the coordination center, commander can also see the marker added by Rescue 2. When the map tool is used in an infrastructureless environment, the order of the events become critical for the first responders to understand the situation. Our second component, the consensus protocol, achieves it with high efficiency.
We show a demo of our experiment to model our consensus procedure for a strong map update consistency in an intermittently connected environment. Our scenario environment is a subset of the city of Helsinki. In particular, it includes the major part of the southern major district of Helsinki. The regioning of the map is captured in a hierarchical namespace, with the levels following the city, major district, district, and neighborhood structure. Our city subset includes 3 districts, and the total environment is 4,500 times 3,400 square meters. We place several hundreds of mobile users in the area. We have 30 first responder users, 10 responsible for one of the 3 districts, each placed and moving around in the neighborhoods of the district that they are dealing with. We add additional benevolent mules to help with better delivery. There are 500 civilians and 50 vehicle mules. Only first responders participate in consensus sessions and are generally interested in updates from regions that they're dealing with. Each first responder creates 3 updates in the first half hour of the experiment at 10-minute intervals, so we will have a total of 90 updates eventually. The updates are data in form of flags or pins and shapes on the map that belong to a location and a region and have information associated with them. The updates created by first responders are to add markers as flags, as well as removing or editing existing flags. As shown, different first responders create their updates at different times without coordination with the server. After some time, our system ensures that all updates are applied in the same order, and all first responders eventually have the same view of the map. Please see our corresponding presentation for more details on the algorithms for achieving consensus. The dissemination of information is done through percolation and epidemic propagation. The user nodes are dispersed randomly in the environment. We use a simulated and randomized map-based mobility pattern for our experiment. Every user has a wireless range for D2D communication, and vehicle mules have higher wireless range. The 30 first responder nodes are marked with the letter F. As shown here, there is no network infrastructure, and information dissemination relies only on users opportunistically exchanging messages. As we see, mobile contacts or links pop in and out of existence so rapidly, mostly last less than a minute, which shows the high level of dynamicity of our disaster scenario. To show consensus completion, we visualize three main quantities for the first responder nodes. The blue bars will show relevant agreement completeness, which is how many slots in the strongly consistent map view get filled with agreed updates for regions relevant for the first responder. The green bars will show total agreement completeness, which is how many slots in the strong view get filled with agreed updates at the first responder regardless of relevancy. The red bars will show the buffer occupancy at first responder devices in their phone storage in our application. Here we show two scenario progressions. The right-hand side map shows our method, which uses name-based interest profiling. For comparison, we compare it to a more state-of-the-art solution shown on the left-hand side map. Both scenarios here have the exact same mobility patterns as shown. Our experiment time is 12 hours, and we show with an hour-by-hour snapshots. As we see here, our solution uses much less buffer capacity at first responders with much slower growth rate. This makes sure that first responder mobile devices do not get overloaded with too much content, especially those that are not relevant for that particular first responder. As new consensus decisions are made, shown with blue and green bars, we see buffer occupancy decreases as well. This is because contribution messages related to that consensus decision get removed from the buffer, which helps with additional bidder efficiency in our system. In our solution, we see much higher completeness. This shows that the same view that different first responders see on their map is completed and built to a much higher degree. Also, our use of interest profiling makes sure that blue and green bars are equal size at each first responder, which ensures relevancy. Our method enables effectiveness and efficiency for first responders and helping them to end up having the same view of updates that they all agree with, even in an infrastructure-less environment.
The text messages are much smaller and faster in delivery compared to the voice messages. However, they request first responders keep an eye on the screen. To allow them operate the system eyes-free, we designed a distributed text-to-speech solution.
In our demo, we use Tacotron, which is a recent generative text-to-speech model based on deep learning. Tacotron synthesizes speech directly from characters. It has an end-to-end property, which means that it is directly trained by text audio pairs. The Tacotron architecture is shown on the right. It has been shown that generation quality of Tacotron is significant. It can achieve an outstanding mean opinion score. Tacotron has been applied to many languages, including English, Chinese Mandarin, Korean, but in theory, it can be applied to almost any language. However, Tacotron is not distributed, so our focus in this demo is to implement Tacotron in a distributed manner. We use N devices to implement distributed TTS. Here is the topology of our demo, which consists of one master device and multiple helpers. The master device behaves as an access point. Helpers, which are just nano developer kits, are connected to the master device via Wi-Fi. Master is responsible for pre-processing text, splitting the long paragraphs, sending text to helpers, and receiving generated speech from helpers. Each helper runs a pre-trained Tacotron model to convert text to speech. Here's a snapshot of our demo setup. We can see in the picture three JSON nano keys as helpers, and a computer is responsible for master device. In our demo, text is split into multiple pieces. Each has up to 128 characters. We use a pre-trained Tacotron model. Task completion delay is a key metric in our experiment and includes, first, communication duration between master and helpers, and second, processing time at helpers to convert text to speech. Our experiments show that the distributed TTS significantly improves task completion delay. Here is the interface of our distributed TTS demo. We enter the input text on the left pane. We also enter the IP address of helpers and the number of helpers to process the tests. After master receives the speech from all the helpers, the right pane will report the task completion delay. The interface also plays the generated speech. Now, let us look at the scenario that there is only one helper.
Decode base64 to file using the free online decoder, which allows you to preview files directly in the browser, as well as download them, get the hex dump for any binary data.
We can see in this scenario, the task completion delay is about 15.54 seconds. Now, let us set the number of helper to 3. In this case, the task completion delay is about 5.94 seconds. So as see, task completion delay reduced a lot when the number of helper increase.
Efficient routing is not easy in infrastructureless environments. The last component we developed this year is the dynamic routing protocol.
In this presentation, we will show a demo of our binary straight distance vector routing protocol, which will comprise of 3 views. In the topology view, we will show the topology of the overall network we are working with. In the control plane view, we will show the forwarding table entries at each node in the network we are working with. And finally, in the data plane view, we will show the progress of a file transmission happening between any two nodes at a given time. In this scenario, we will initialize the following network topology comprising of 5 routers. We will demonstrate that the routers can find the primary path highlighted by the bold black lines using the shortest path algorithm, and how that is reflected in the forwarding table entries at each router. Furthermore, all these entries will have an active state as there is no node failure in this network. In this demo, each of the 5 routers are initialized as an independent process, and they start a series of connection requests to set up the topology we showed in the previous slide. By looking at the forwarding table entries, we can see that the routers are able to find the correct primary path using the shortest path algorithm. And for each entry, dest is the end destination and via is the next hop, and all of them have an active state of 1 since there are no node failures in this network. In this scenario, we take down the router R5 from our network to demonstrate what happens during node failures. Since R5 had connections that formed part of the old primary path, the new path, shown by the bold black lines, now needs to be recomputed among the remaining active routers in their active connections. This is achieved by exchange of a series of update messages starting at the direct neighbors of R5, which contain their updated distance vectors reflecting R5's failure. This information is exchanged with their neighbors and then their neighbor of neighbors. In this demo, like the previous scenario, the original topology is first initialized. After that, the router R5 is failed, which causes an exchange of a series of update messages between the remaining active routers to recompute the new primary path from among the remaining active connections, and also to reflect the change of R5's failure in the network in the forwarding table entries. For example, the forwarding table entry for R5 at R1 has its state updated from active to inactive, that is from a 1 to a 0. In this scenario, we look at what happens during file transmission between two nodes at a given time in our network. We assume there are no node failures and that the routers have unlimited buffer capacity available to them. To demonstrate this, we will send a file called Windows MP4 from R1 to R4. The file has a size of approximately 672 kilobytes, and our MTU is fixed at 5000 bytes. Therefore, the buffer at each router will hold at least 137 packets. In this demo, after the original topology is initialized, router R1 initiates the file transmission by loading the file Windows MP4 onto its own message buffer. Once the buffer is fully loaded, the transmission begins and all the loaded packets are forwarded based on the forwarding table entries at R1 to R5, which then forwards these packets to their destination R4. Since we are dealing with unlimited buffers, the transmission is almost instantaneous, and once it receives the complete file, R4 clears its message buffer. Finally, we look at what happens during a file transmission between two nodes at a given time in the network when node failures are possible and the routers have limited buffer capacity available to them. To demonstrate this, we reuse the file transmission of Windows MP4 from R1 to R4, but in this case, during the transmission, we take down R4. After a short period, we will resurrect R4 again so that the interrupted file transmission can resume. Like the previous scenario, the file transmission begins when R1's buffer is fully loaded with chunks of the file Windows MP4. Note the transmission is slower in comparison due to the routers having limited buffer capacity. During the transmission, we take down R4, causing the forwarding table entries of the remaining routers to be recomputed and the file transmission to pause momentarily. When R4 is brought back up again, the file transmission resumes, the forwarding table entries are recomputed again, and R4 clears its message buffer on receiving the complete file.
These components are now implemented separately due to the current situation. As future work, we'll integrate them and show a unified system in the next year. We'll also request more first responders try our system, and we'll keep improving the system based on the feedback. Thank you very much for your attention. In case you have any questions, please do not hesitate to contact us. We have listed our emails at the bottom of the slide.